elc138, worksheet 15. Okay. This is a continuation. This is your practice worksheet from the last worksheet. On the last worksheet, we designed a voltmeter, and we worked through the example of how to design it. And on this worksheet, I'm giving you different ranges to design, which would correspond to switch positions. On those, we have to select the range. And so basically, I'm asking you to find the series resistances that you'll have to use. The meter movement's different. It's now 600 ohms and 1 milliamp. So you want to design a voltmeter for 10 volt range using that coil, 600 ohms, 1 milliamp. Then do it for 20, then do it for 150, then do it for 700. And so you have a pretty good understanding how voltmeters are designed and how they're built. And anytime you pick up one of the old analog ones, you'll know what's inside. For 5 and 6, we're going to use the same meter movement, but this time we're doing ammeters. And so you want to find the shunt resistances required. 8 through 12. Consider the following circuit. Sketch it out. Make sure you get it right. I guess you could send me an image of what you've got in LT Spice to see if I agree with you. If you have any trouble, you should be getting to the point where you can sort of just go through these net lists, come up with a circuit. Then what I want you to do is go in and tell me what the normal is. Node 1, 2, and 3 voltage, because this is what you would do troubleshooting. You would probably just measure the voltage. And short your R1, or open your R1, see what your voltage is changed to. Short your R2. Remember, each time if you open R1 you get the readings, then put R1 back. When you short R2 and get the readings, remember to remove the short when you open R3, etc. So only have one fault. Most of the time in troubleshooting, you're looking for a single point of failure. While it's true you can have multiple failures, but you generally only have one failure at a time in a circuit. So that's sort of your troubleshooting mentality, is what one fault would cause what I'm seeing. Okay? If it's something that's been running, that's what you're looking for. If it's something that is not been running, has not been proven, then yeah, it's something that somebody built, yeah, you could have multiple faults. But generally speaking, let's get you good on troubleshooting, looking for one fault. So only have one fault at a time. Please put it back, or else you won't do very well on this part. As long as you put it back. And what I would suggest is put it back and rerun your normals. And that way you know your circuit's back to normal, whatever normal is. And then you can go in and then go back down. And that way you're sort of testing and helping yourself. All right. Sad. These are the problems where I would build a circuit, have it covered up. So all you could do is come in and take voltage measurements. You can see what fault I put in it. The nice thing about doing it virtually or now online is I've got this circuit and I have bugged it. So using a meter, this would get you meter practice. And you can always pre-analyze a circuit up front, just like you did in the previous problem. And a matter of fact, that's probably what you'll have to do in this one, because I want you to start thinking what one fault will cause what I see in terms of voltage readings. And that will make you an excellent troubleshooter, and that is something that is desperately needed. Desperately. Okay, so what I did is I built the circuit. I built it, I double checked, make sure I built it right. I built it in LT Spice, and I then put a bug in it. And so for my bug, your readings, and I'm going to type them in here. I think I can type in here. Let's put it at the bottom. Okay. Okay, my voltage from 1 to 0 equals 11. Okay, so in my faulted circuit, you get two readings. You get voltage from 1 to 0 and from 2 to 0. And my voltage from 1 to 0 is 11 volts. And my voltage from 2 to 0 is equal to 8.9 volts. So those are your fault conditions. I made the measurements for you. Now what you've got to tell me for this problem is, what did I bug? And a bug can either be an open or a short. So don't just give me a resistor. Give me a whether it's open or it's shorted. Okay? You know how to do that. You can do it both ways now. And that will be great. 16 is a safety question. It's something I've come to believe in my life, that when you have a multimeter, you use your multimeter every day. You've got your leads in your multimeter, but what happens when somebody picks it up? So I've come to the conclusion that you should remove your multimeter leads, because it's less likely somebody will pick it up and use it inappropriately or incorrectly or in a dangerous fashion. Generally with safety, you try and make things so people have to make two mistakes to get hurt. And if they have to put the leads in and then they have to put it in the circuit wrong, that would be two mistakes. So in order to help you in terms of safety for your whole life, think about that. How can I make it to where somebody has to do two things in order to hurt themselves? And meter is a very easy one. Okay, last one, PLC application. We wish to design a variable current source for a PLC input card. The source voltage is 13 volts. The current will vary based on rheostat setting. Do you remember what a rheostat is? Okay, between 4 and 20 milliamps. So I never want my current to go to 0, which would be easy. I want it to go to a minimum setting of 4 milliamps, which would be, in terms of resistance, the highest resistance in the circuit. And I want it to go up to 20 milliamps, which would be the lowest resistance in the circuit. So I need to come up with a fixed value for a resistor, and I need to know a rheostat value. Now my rheostat value can go from 0 to a max. So basically, when your highest current setting, your rheostat is out of the circuit, it's a 0. So your fixed resistance will set your 20 milliamps, and then that fixed resistance plus the series value of the rheostat will set your 4 milliamps. Okay? Now this is a design problem, so you'll come up with these perfect numbers and these perfect resistors that will make this work great. Okay, but unfortunately you can't just get everything you want. So in terms of the availability of resistances, what's the closest common value? Okay, so what's the closest value of resistor to what you calculated that you can get? And what's the closest value to the rheostat that you calculated that you can get, or potentiometer? Potentiometer set up as a rheostat. The other thing you need to do in this problem is go ahead and do the power. How much power will the fixed resistor have to dissipate, worst case? And hopefully you've got a hint on that. Okay. That is your mission. This is actually a good problem because electronic technicians sometimes do have to come up with ways to vary signals and make them happen to test equipment or whatever. And for PLC, there is such thing as a 4 to 20 milliamp input card. And sometimes we want to make sure it's working right, see what it reads, see what number it turns the current into, that kind of thing. So this is actually a practical application. Anyway, that is pretty much it for this worksheet. So in Spice, the way I do this is I do my 13 volts, and you can play with two different resistors. And you can short out the one, and then you'll know. And you can verify it, or you can calculate them manually. It's up to you. Anyway, hope this helps. And this is a relatively short video, but it reinforces an earlier one. And thank you for watching.